Hey guys, this is Arno, and today we're going to talk about plasma propulsion. Now the first thing we need to consider before we even begin to talk about plasma is the rocket equation. So the rocket equation, which is this, was derived in 1903 by a Russian scientist of the name of Konstantin Tsiolkovsky. And it's very likely that you have seen this equation before, because a typical undergrad problem is to derive this equation from Newton's law, Newton's second law. So the rocket equation, put in this form, yields a formula that allows us to express the change in velocity of a spaceship in terms of the exhaust velocity of the propellant, the mass that is ejected from the spaceship, times ln of the ratio of the initial mass of the spaceship over the final mass. Now what's an important thing that we can conclude from this equation is we see here that the mass to change of velocity ratio is an exponential function, meaning that a huge change in mass will result in a small change in velocity. Meanwhile, on the other hand, a change in the exhaust velocity will be linearly proportional to the change in velocity of the spaceship. And this is the very fundamental idea of plasma propulsion, because the rockets that we currently use do not allow for high values of VE. Therefore, if we want to change velocity fast, we need to make a huge account in the change of mass. And this is why we say that chemical rockets are highly inefficient, whereas on the other hand, plasma propulsion, plasma engines allow for high values of VE. Therefore, there isn't a big change in mass needed in order to change speed quickly. And that's why we are going to talk about plasma propulsion more and more nowadays. If there is one thing that you should remember from this video, is this, that plasma propulsion allows a high exhaust velocity and therefore doesn't need a big change in mass. That's the advantage, and this is why so much research is being done about plasma propulsion nowadays. Now, of course, this is a very simplified model, but even when adding the drag and gravitational terms that are taken in account when doing those calculations for precise results, this behavior remains. Okay, we are now ready to look at a few examples of plasma thrusters. Now, when speaking of electric propulsion, there's really two types that involve plasma and their properties. There's electrostatic propulsion and electromagnetic propulsion. We'll begin by talking about electrostatic propulsion. Now, the basic idea of electrostatic propulsion is that you take a plasma in equilibrium and you apply a voltage to it. You give a certain potential across the plasma. And this, by effect, and as we know from E and M, will shift the ions in a certain direction. And in order to maintain this voltage across here, you send a source, an electron source, close to the anode around here, so that as soon as the ions pass the anode, they are immediately neutralized by adding an electron to them. So this effect has two important purposes. The first one is to maintain the voltage across this zone, because if this wouldn't happen, well, the particles would shift in order to cancel the voltage, the electric field within this zone. And the second effect is charge conservation, because if neutralization wouldn't happen, a charge would build up within the spaceship, and therefore the electrostatic propulsion will become less and less effective. Now, the advantages of such an engine are really twofold. There is the efficiency. This engine is very efficient, and it has a long lifetime. The limitation of this electrostatic thruster is that this zone, called the plasma screen, really only allows for a certain amount of ion at a time, due to the fact that each and every one of those particles has an effect on the overall electric field within this zone. There is only a limited amount of ions that can be there at a time, and therefore very, very small thrusts compared to chemical rockets